Okay, so this is about bandwidth. Yeah? So the frequency of changes in the measurand. Measurand is the parameter that we want to measure. At what range can the sensor measure? So ideally, we would like a sensor which has a wide band, that it can measure from very small frequency rate of change into very high frequency rate of change. But no such ideal sensor exists. So in reality, usually they work in certain bandwidth. So below that frequency, below a certain frequency, the sensor cannot measure it. Or when the measurement has a frequency of change higher than certain frequency, the upper um, frequency, yeah, the upper frequency, then they cannot measure it as well. Okay. So this is the typical sensor has a band pass, what you call it as a band pass response. Yeah. So this is another tensor terminology in terms of its dynamic response. Yeah. So for example, if we have a square wave, and then usually we have a delay. Yeah, we call it propagation delay. So the sensor cannot measure it exactly at the same time when the stimulus, yeah, or the stimuli appears. Is what we call as propagation delay. Then there is also low frequency roll off, ringing phenomena. Yeah, then what happens when we measure something, for example, uh, beyond its bandpass? Yeah? Then the measurement cannot be perfect. There will be some distortion to the measurement value. For example, here we have FL1, which has in this curve A, yeah, the A curve, it has wide bandwidth. But then B has a narrower bandwidth, the bandpass, yeah? And C has even narrower bandwidth. So if we put a pulse signal measurand, or pulse signal stimuli into the sensor, this is what happens when it is applied or implemented with the sensor that has the A curve bandwidth, then it can follow almost quite well. Yet the time delay here is very small, the delay. But if we put it into the sensor which has the B frequency band, the free B bandwidth, yeah, then we have here distorted output, and the distorted output because the the sensor cannot follow all the higher frequency component of this pulse signal. A pulse signal, maybe later you will learn in signal and system in semester 5. A pulse signal has many frequency component, not only a single component. If sinusoidal signal, I should draw it. A sinusoidal signal has a single frequency, right? A sinusoidal signal has a single frequency f. Yeah. So if this is the period of that the sinusoidal signal, then frequency is 1 over t. Okay, then so this is usually why is expressed in this the amplitude A multiplied by sin omega t, yeah, omega t, where omega equals to 2 pi multiplied by the frequency. Okay, but however, when the signal is passed like this, it contains not only a single frequency like this, but instead it has also higher frequency signal and even further higher frequency, not only one or two, three frequency components, but it is a spectrum of frequency that form that pulse. Okay, and also you have when you have an impulse signal, impulse is very sharp change. It's impulse signals like this, very sharp change in uh, time domain. Then the frequency domain will have a wide spectrum frequency, yeah, domain. So this is you will learn. I believe you are also learning it in technical mathematics by Pak Fatoni, yeah, the conversion between time domain signal to frequency domain signal. But you will learn it in more detail in signal and system course. So when our sensor has like this, yeah, in a curve has a wide bandwidth response, then it can follow almost all the frequency component of this pulse signal. But when it has narrower and even narrower, for example, in this response in the curve C, then it cannot follow the higher frequency component of the signal. As a result, before this change occurs, then suddenly the pulse ends like this here, and then it has to start decreasing. So the steady state value cannot be reached by this sensor with a response of curves of C. Okay, drawing first. So now let's go to the types of transducer in quickly, yeah, overviewing it. If a transducer is a device that converts a primary form of energy to an electrical energy for the purpose of measurement or control, then we have transducer versus electrode. In transducer, it converts the form of the energy of the signal. However, in electrode, like being used for ECG, electrocardiography, EMG, electromyography, or EEG, electroencephalography, the signal is still, the energy form is still the same, basically electronic, although the carrier is different. In the body, the electronic signal is being carried by ions. So actually, it cannot be called electronic anymore. It should be called as ionics. And it can be positive ion or negative ion that acts as the charge carrier. In the wire, however, when it is converted into wire, so the electrode will convert that into electronic signal. It's basically the same form of energy, electrical. However, the charge carrier will be mostly electrons rather than positive or negative ions. So this is the function of electrode, is to convert ionic signal into electronic signal. Transducer, on the other hand, is more different form of physical signal. Yeah, for example, pressure transducer change pressure into resistance. Thermistor change change measurement into electrical resistance, yeah, to measure the temperature. So primary transducer changes the real world parameter into electrical signal. Then the secondary transducer convert this electrical signal further into another electrical signal in the form of analog or digital. So we can say that amplifier, for example, electronic amplifier, can be set as a secondary transducer because it converts the same electrical signal into another electrical signal, voltage in this case, but amplifying it. Yeah? So it is called as a secondary transducer. Later, we also give another example called as Wheatstone bridge, which converts resistance change into voltage change. Both are electrical parameters, but they are of different types of parameter. Yeah? In resistance change, it is resistance, then converted into voltage change. We can also then classify analog to digital converter can also be said as secondary transducer because it converts electrical signal in the analog domain into digital domain. So this is a typical electronic transducer system. We have the input signal measurement, we have a sensor, and usually there is a secondary transducer here before it goes to a microcontroller for signal processing or for communication. Then it is being displayed or goes into the network for transmitting to different places in the world. So many biomedical parameters rely on measurement of size, shape, and position of the organs or tissues. Here in this case, then we need displacement transducer. So the primary transducer, for example, for this is based on the converted electrical parameter, yeah, and we can classify them as resistive transducer. So then this displacement or other physical parameter is converted into resistance change. Then we have inductive transducer where it is converted into inductance change, which further converted into voltage or current change. Capacitive transducer is based on the capacitance change. Piezoelectric transducer is voltage change from mechanical strain converted directly into voltage change. Secondary transducer is, as I mentioned earlier, Wheatstone bridge, converting resistance change into voltage change, and then amplifier. Voltage into voltage, but putting an amplification of it there. So this is a Whetstone bridge. Yeah, maybe I will not go into the detail of it. You will be learning this in semester 4, yeah, which convert resistance change. So you put the resistive sensor, resistive transducer in one or two, or sometimes also all the four arms or bridges of this Whetstone bridge. Then the resistance change will be converted into voltage difference between the two ports here, between EC and ED. Okay. This is the derivation. Okay. I will not go into the detail. Just go through. If you want, you can read this slide. I have uploaded it into the Google Classroom. This is the example of resistive transducer, potentiometer. It can produce output potential voltage in response to input. So in this case, or in this case, it is displacement. So if it is like this is a rotational potentiometer. It converts the displacement in the knob into resistance change. We can also have linear potentiometer, like this one. So here, linear potentiometer. In this case, when the shaft displays linearly, the resistance will also be changed in this way. A slide potentiometer is also a linear potentiometer. So another resistive transducer is strain gauge. This change or convert mechanical strain. Mechanical strain, what is mechanical strain? You will learn later in the semester 4 also. Mechanical strain is the relative change in length in an object, in a structure, compared to its original length, delta L divided by L0. And delta L is basically the current length minus the initial length divided by the initial length. This is the definition of strain. Okay, so a strain gauge produce change in the resistance proportional to the applied mechanical strain. So the force applied is either compression or tension. So usually when it is compression, the strain will be negative. If it is compression, the L will be less than L0. So if it is compression, epsilon will be negative. But if it is tension, tension means it is being stretched. Then the L, the current L, will be larger than the L0. Epsilon will be positive. Okay. So what are the application? Application is like this for respiratory monitoring. When it is put in the chest, and we can measure the contraction and the expansion of the chest, which is related to the respiration. We can put also in weight scale. So this is something which maybe you have also in your house, yeah, to measure your weight. So it has basically strain gauge as the transducer to convert the mechanical strain due to your weight into resistance change and further into voltage, and then process. And then you can read the reading, yeah, after it is being calibrated, of course. Like this, also feedback hand glove for game control, or also can be used for stroke rehabilitation. So the principle is like this: when it is being stretched, the resistance will change because any of these three parameters change, either the length or the cross-sectional area of the resistor, or otherwise the resistivity also change. Okay, I will not go into the detail of that. We will discuss this in more detail in semester 4. So the important parameter to be used in the resistive sensor is the GF, what we call as the gauge factor. So this basically represents sensitivity, because usually when we calibrate a strain gauge, we will calibrate it. The x-axis will be the strain, and the y-axis will be the delta R over R. The resistance change as a function of the initial resistance. Yeah, delta R here is or equals to R minus R0 divided by R0. So when we have the response, the calibration curve, the gradient will be this gauge factor equal to this one. delta R over R divided by strain. Basically, this is the gradient of this calibration curve. So when you have a strain gauge which has a high gauge factor, it means it has a high sensitivity. Is it good? Maybe yes, maybe not, depending on the situation. So in actual measurement, our concern is not only the sensitivity alone. We are also sometimes concerned with the resolution. Resolution means, again, you remember the definition on the previous slide, the slightest change of the measurand, measurand is the parameter being measured, the slightest change of the measure that can be measured. So sometimes high sensitivity strain gauge cannot measure very small strain. So it means the resolution is not that good. Yeah, so it depends. It depends on the situation. So you have to read all the parameters carefully. Okay. This is a type of strain gauge. Yeah, this is the wire here is functioning as a strain gauge. Then this is put into a Whetstone bridge configuration, and this is the bonded strain gauge, like this. Yeah, so usually this is how it looks like. Yeah, with the meandered resistor, so that then the R0 can be made, the knob which we call as the nominal resistance can be made very large. Yeah, and then usually the gauge factor will also improve because then the delta L and delta R can be contributed from each of this meander. Okay, so this is more also geometrically more space efficient because you don't need to have very long strain gauge to measure to have a high sensitivity. Otherwise, like this, you put into a helical wire, wound it into some core, and put it in the diaphragm. And strain gauge is usually rugged and cheap, low mass, available in many configurations and sizes for different applications. There's even many companies specializing in developing strain gauges and then sell for different applications. And one of the drawbacks of strain gauge, it is also usually sensitive towards temperature change. And this can be overcome by using a dummy gauge wire that is exposed to temperature but not to the applied strain in a Whetstone bridge, for example, like this. So this is a configuration where we put 4 strain gauges in a Whetstone bridge. Then this is how in the mechanical configuration, for example, in your balance, digital weight scale balance, it usually the 4 strain gauges are being put into the load cell, yeah, into a beam structure, and to measure 4 different strain at the same time, and they are being put in electrical circuit in a Whetstone bridge configuration. So this is the resistive transducer configuration. Yeah, E output -10. I'm not going to detail this, maybe later in semester 4. Then going to the next type of transducer, which is called as inductive transducer. This is change, yeah, the flow electric of current create a magnetic field. Based on the magnetic field, for example, due to the very close iron, for example, then the magnetic field will also change. The change in the magnetic field can be measured in terms of current or voltage. Then we can use it as a displacement transducer, for example. Now this is an inductive, how inductive transducer look like. Yeah, so it can be in self-inductance like this, or mutual inductance like this, or differential transformer with 3 different transformer. So capacitive transducer, remember this formula, maybe you learn it in physics. Capacitance equals to epsilon 0, the electric constant of the free space, epsilon r, the relative dielectric constant of the insulator, multiplied to the area of the plate of the 2 electrodes. X here is the distance between the 2 electrodes. So when any of these 3, epsilon r, epsilon 0 we cannot change, but we can, when epsilon r or the A or the X changes, any of them, then we can use, then the C will also change. So it means we can use it also to detect as a displacement sensor, very sensitive displacement sensor, very high resolution displacement sensor, to measure the X change. We can also use it for chemical sensor. by measuring the epsilon r, the changes in the epsilon r of the medium of the fluid, for example, of any material flowing between the two electrodes. We can also use as displacement sensor by using the A in the different in a more high dynamic range displacement sensor by measuring the changes of the interacting area between the two plates. So something like this, yeah. Plus Q minus Q, and then usually we use secondary transducer. We want to change the capacitance change into voltage change using like this. Here in a circuit, remember your electrical circuit. This put it in series with a voltage source, and then we measure the current flowing through here and put it in an op-amp, for example, and the current flowing will be equal to C dVc dt. So capacitive sensor can have very high resolution as a displacement sensor, even less than 0.1 nanometer. Right? This is very small. It means very high resolution, yeah, because the displacement that can be measured is very small. The dynamic range up to 300 micrometer, high long-term stability, less than 0.1 nanometer for 3 hours, so it means it doesn't drift. The bandwidth is 20 hertz to 3 kilohertz, a quite wide bandwidth. So here, when you use it as a diaphragm, so for example, some types of microphone also is based on capacitive transducer. Based on the diaphragm, two plates, one acts as a diaphragm that can vibrate due to the air vibration. Basically sound, when we measure sound is basically vibrating pressure, right? Vibrating pressure of air in front of us. When we make a voice, the air vibrates longitudinally, yeah, like this, with different air pressure, creating different air pressure. And then this can be captured by a capacitive transducer in the form of thin metal diaphragm. The diaphragm will vibrate. The other end will be fixed, will be more rigid so that it doesn't change. But the distance between the two electrodes will change also as a function of this vibration. And then this capacitive change can be converted into voltage change, and further we can recognize that voice. We can capture or record that voice or sound. It can be used like this, yeah. So for as a rotational motion sensor, when one is stationary, the other is movable, or otherwise as a differential capacitance, P1, P2 like this. Yeah. Piezoelectric transducer measure immediately converts strain, remember what the definition of strain, mechanical strain, into voltage change. So this can be used for physiological displacement or recording heat sound, hard sound. Sorry. Yeah, so when an object, piezoelectric material subjected to a mechanical strain, being compressed or being stretched, it will generate voltage. Yeah, or the opposite is true also. When we apply a voltage, it can change its physical dimension. So it can be used, for example, in phonocardiography, measuring the external body surface and internal intracardiac pressure. Detection of Korotkoff sound in sphygmomanometer, in blood pressure measurement. Measuring physiological acceleration. Provide an estimate of energy expenditure by measuring acceleration due to human movement. So piezoelectric transistor, this is how it works. So it's like this. It consists of, can be modeled as a stack of the electric material. The electric material similar like capacitance. Yeah, charges are being polarized into two sides of the electric material. That's why it's called dielectric. I mean double polarity. The Q, the charge polarity Q, like the charge polarization, is expressed as K equals to Kf. K is the piezoelectric constant, the coulomb per Newton, and F here is the force Newton. The higher the K, then the higher the piezoelectricity. It means it can also have higher sensitivity. For quartz, it's 2.3 picocoulomb per Newton. For barium titanate, barium titanate, the chemical formula is like this. So, barium titanate. Okay, barium titanate is 140 picocoulomb per Newton, so very high. So we can model a piezoelectric as a capacitor, yeah, like this. Q divided by C equal to Kf divided by C, Kfx divided by epsilon 0, epsilon r multiplied by A. X is come from here basically, from this formula. So for example, if we have a sensor of 1 square centimeter area, 1 millimeter thickness, when applied force due a 10-gram weight, the output voltage will be V equals to 0.23 millivolt per quartz, with a K of 2.3 picocoulomb per Newton, and 14 millivolt per barium titanate crystal. So this is how we model it in electrical circuit, yeah, with a leak resistance here, Rs, and then we model it as a parallel capacitance of CS, sensor capacitance, cable capacitance, amplifier input capacitance, and the amplifier input resistance. So the Q, the charge equal to voltage multiplied by capacitance, equal to Kx. So the voltage output, the output voltage equal to K, the piezoelectric coefficient multiplied by X, the displacement, divided by the charge. So the leak resistance will cause a decay, yeah, remember, for the first order response. And then the time constant will be equals to tau equals to RC, yeah, for first order system. And this is how it looks like, a piezoelectric transducer, yeah, something like this, very thin, can be used as a pressure to electrical transducer or mechanical strain to electrical transducer. Temperature transducer. There is a thermocouple, thermoelectric device, resistance temperature detectors, thermistor, basically as a resistor that is sensitive towards temperature. Yeah, this is the formula, RT equals to RS exponent. So it is nonlinear. Resist RTD is from metal. Yeah, this is a formula also usually expressed and as a polynomial, but usually we only use the linear terms, so 1 plus a alpha 1t. The other terms, because the coefficient, if they are small, then can be neglected. In radiant temperature sensor, we measure the radiation, the black body radiation coming from the object, and measure it without contact. And then IC temperature sensor, using the effect in the silicon device. So this is thermocouple. Thermocouple uses the physical law called as the Seebeck effect. Yeah, based on the Seebeck, when you have two junction made by two types of metal here, and one is put as a reference junction. So the delta V, the voltage, there will be a voltage the difference between the two junctions, which is a function of the temperature difference between the two junctions. So this is from Seebeck effect. When two different metals are joined together at two junctions, electromotive force or potential basically is generated. The amount is different based on the temperature change. Peltier effect is when two dissimilar metals are joined together to form two junctions. EMF is generated within the circuit due to different temperatures of the two junctions. And the other way around also works. So when we apply voltage changes, voltage difference between the two junctions, there will occur also temperature difference. And that's why Peltier effects also used as a coolant, as an actuator for cooling, for controlling temperature. Fast response, but it has small output, low sensitivity, and need reference temperature. So this is thermistor, and this, maybe you are familiar with it. Yeah, when you can use it as a cheap temperature sensor, either with PTC, positive temperature coefficient thermistor, whose resistance will increase with temperature increase, or as NTC, negative temperature coefficient thermistor, whose resistance will decrease when temperature increase. Yeah, so opposite. Heavily used in biomedical application, very small. Base resistivity is 0.1 to 100 ohm meter, and excellent long-term stability. Then RTD, this is normally used in industry because it's quite expensive. Made from metal, from pure material, platinum, nickel, or copper. Fine coil wire wrapped around a ceramic glass. and then you put inside a sheet probe. So this is the comparison. And we have also IC made from semiconductor. Usually it has the best accuracy and sensitive to shock, but and can be made low cost because it is made in batch, very linear and faster than RTD. But for high temperature, usually we use thermocouple in industry, for example, like that, yeah, minus 400 to 40,200 degrees Fahrenheit. And RTD also for industry, but for biomedical, usually we use thermistor. So this is the formula for thermistor. And in this one also is radiation thermometer, which is also used in biomedical application to measure the temperature of the subject without having to touch on it, yeah, based on the black body radiation emitted by the object, by an object. Application can be for breast cancer, mammography, thermography, determining the location extent of arthritic disturbances, measuring depth of this tissue destruction due to frostbite and burns, various peripheral circulatory disorder. So this is based on uh, radiation thermometer, the black body radiation. So this is the law governing the equipment. So black body radiator is an object which absorbs all incident radiation and emits the maximal possible thermal radiation. So usually for human body, our temperature that is around 37 degrees Celsius, right, emits a black body radiation in the range of 8 to 12 or 14 micrometer. So then we have to use detectors that is sensitive in this wavelength. So this is mid and mid-infrared wavelength. So this is how it looks like, a system of radiation thermometry. This is the infrared detector, and usually it has a phase-sensitive demodulator, yeah, using a phase lock amplifier, AC amplifying phase-sensitive, this one with chopper. So because otherwise it is just a DC signal, right? We modulate it first using a certain frequency here, and we demodulate later so that we can get rid of the noise. Then fiber optic temperature transducer, this measure temperature based on light transmission change, yeah, due to the, for example, expansion or at the mirror here. This is how it looks like, very small, can be made very small, so we can use fiber optic temperature transducer to measure temperature at very specific location. And optical measurement is also being used in biochemical analysis in the lab. Yeah, when we go to some laboratory, clinical lab, they measure the component in your blood using spectrophotometry. Here, a lamp is used, and then using some filtering, the blood sample is put in the cuvette. Then the transmitted light is being measured again using spectrophotometer grating, and then a white light is spread into spectrum, and the spectrum will be different based on the sample, yeah, on the sample chemical condition. Now this is being miniaturized into LED and phototransistor. And optical measurement also can be used for SpO2 measurement. Yeah, here pulse oximetry, very important now to measure hypoxia, for example, to detect hypoxia for COVID-19 patient in COVID-19 disease patient. Yeah, measure the ratio between the transmission of light in the infrared region and compare it with the transmission of or reflectance of light in the red wavelength region. Yeah, and this is the optical radiation source. And this is the more detailed theory which you will be learning in semester 4, I believe. I think that's all. So we have about 10 minutes. I would like to use it as for a short quiz. Okay, short oral quiz. So please